Hello everyone. Today we're going to look at related rates. Oftentimes variables will vary with respect to time, even if t is not in the function. We can find the rate at which the variable varies, which is also known as the derivative, by using implicit differentiation. So let 1/2 x squared plus 3y squared minus 4y equal 12. Find dy dt when dx dt is 3, x is 4, and y is 2. So when it comes to related rates, just like with implicit differentiation, the denominator of your derivative is really, really important. So here, my variable is t. So every time I differentiate a variable that is not t, I need implicit differentiation, which means the chain rule. Okay? So 1/2 x squared, I differentiate it as if x were my variable. So I bring down the 2, and I'm left with 2 times 1/2, which is 1 times x. But x is not my variable, t is, so I have to multiply it by its derivative, which is dx dt. The same thing goes for 3y squared. First, I differentiate it as if y was my variable, and I get 6y. But my variable is t, so then I have to multiply by the derivative of y, which is dy dt. I have to do the same thing for my 4y. The derivative is negative 4, and then I have to multiply by dy dt. Derivative of 12 is 0 because it's a constant. So to clean it up, I have x dx dt plus 6y dy dt minus 4 dy dt equals 0. Now I plug in everything I know. Dx dt is 3, x is 4, y is 2. I don't know dy dt. And now again it becomes an algebra problem. I put everything without my dy dt on the other side. So I'm going to have a negative 12. And then I have 12 dy dt, 6 times 2, minus 4 dy dt, and I have 8 dy dt. And then I divide both sides by 8 and simplify, right? 12 and 8 both have a 4 in common, so I get negative 3 over 2. Okay. So it's just like implicit differentiation, except I've got even more variables floating around now. So let's try another one. The area of a rectangle is increasing at 0.35 meters squared per minute. How fast is the length increasing if the width is increasing at 0.02 meters per minute when the length is 10 meters and the width is 6 meters? So the first thing we have to do is come up with the equation that relates these three things, area, length, and width, and hopefully we can agree that that is area equals length times width. The next thing we want to do is differentiate it, and what we're going to do is differentiate it with respect to t because we have time. How fast, that tells me time, and the units also tell me time. My minutes is my denominator, that is dt. So t is my variable. So I'm going to differentiate a equals L times w with respect to t. So the derivative of a is dA dt. L times w, it's a product. I need the product rule. So the derivative of L is dL dt times the other function, which is w, plus the derivative of w, dw dt, times the other variable, which is L. Okay. So again, don't forget, the derivative of the variable is d, whatever that variable is, over d, whatever your original variable is. So derivative of a is dA dt, derivative of L, dL dt, derivative of w, dw dt. Okay, and again, the denominator is going to tell you what your variable is that you're differentiating with respect to. So once we have differentiated, we have to figure out what do we know and what are we looking for. So the length is 10, so L is 10. The width is 6, W is 6, those are the easy ones. And then we have to look at the words and the units. Okay, so the area of a rectangle is increasing at 0.35 meters squared per minute. So the area is increasing, so that is the derivative of the area, which is dA dt. So dA dt must be, what's a decimal point? 0.35. Another way that I can tell that is, again, the units. M squared, meters squared, that's area, per minute, that's time, dA over dt. How fast is the length increasing? That is what I'm looking for. dL dt, how fast the length is changing. I know that the width is increasing at 0.02 meters per second. So dW dt, the rate of change of the width, is 0.02. Okay, so I know everything except for dL dt, which is what I'm looking for. So I'm going to plug those in. So 0.35 equals dL dt times 6 plus 0.02 times 10. Then we do a little bit of algebra, solve for dL dt, and hopefully we can all get that it's 0.025 meters per minute. The unit of length is meter, the unit of time is minute, so meters per minute, and again 0.025. How fast is the slope of the tangent line to the curve y equals 5 over 1 minus 3x changing when x equals 2 if dx dt equals 3? So this one's a little bit tricky if you don't read it carefully. How fast is the slope of the tangent line changing? So I need to know how fast the slope of the tangent line is changing, which means I need to know the slope of the tangent line. The slope of the tangent line is dy dx. So I need to find dy dx, which is the normal everyday derivative that we've been dealing with since, week 2 or whatever. So to find dy dx, I'm going to first rewrite y as 5 times 1 minus 3 to the negative 1, right? Change my fraction into a power. I don't want to do the quotient rule there, right? Because 5 is just a coefficient. So I bring down the 1 for y prime, so negative 5, 1 minus 3x to the negative 2. Chain rule, I have a function, so I also have to multiply by negative 3. So that's where the 15 comes from. So 15 times 1 minus 3x to the negative 2. That is the slope. Now the question is, how fast is that changing? So I need to differentiate the slope with respect to time. Because again, fast means time. So I'm going to take my dy dx, differentiate that with respect to t. So I'm looking at dy dx dt. So again, I differentiate the slope as if x were my variable. So I bring down the negative 2, so I have negative 30, 1 minus 3x to the negative 2. I have the normal chain rule in there, the derivative of the inside, negative 3, and then the derivative of my x. Okay, so that's where I'm getting the 90 from. Whoops. That new power should be a negative 3. Okay. The next step is to plug in the things that I know. So x is 2, dx dt is 3. So I get this guy. I'm looking for dy dx dt, how fast the slope is changing. Okay, so it's already solved for it. I just have to plug that in. And I should be getting negative 2.16. So let's try another one. The shadow of a 30-foot tall building is increasing at the rate of 0.75 meters per minute when the shadow is 40 feet long. How fast is the distance from the top of the building to the end of the shadow increasing? Okay, So the first thing I'm going to do is draw a picture. So I have a building. It's casting a shadow. I know that the building is 30 feet, and I know that at a precise moment in time, it's 40, the shadow. But the shadow is moving, so it's not always 40. It's not constant. So I'm going to call it S for shadow. And the question is, how fast is the distance from the top of the building to the end of the shadow increasing? So that is that distance. And hopefully we see a nice right triangle. Hypotenuses of triangles we like to call C, so I'm going to call it C. Okay. So how fast is the distance from the top of the building to the end of the shadow increasing? How fast means rate of change, means derivative. So I want to know how fast the C is changing. So that's dc dt. So I'm looking for dc dt. Okay, so the shadow of a 30-foot tall building is increasing at the rate of 0.75 meters per minute. The shadow is increasing, so I know the derivative of the shadow, which is ds dt, is 0.75. I also know the shadow at a particular point, again, as 40. And again, the building is 30. So this is all the information I have, and then I have to put it together. Okay? So, again, we have a right triangle, and there is an equation that relates C, S, and the 30. Now remember, S is still a variable, so don't put it as 40. It's S. It keeps changing. So C squared equals S squared plus 30 squared. The building is not changing in height. Right? The building is 30 feet. So when I differentiate, I get 2c times the derivative of c equals 2s times the derivative of s plus 0. Again, 30 squared is a constant, derivative is 0. So as we mentioned before, we know that dc dt is what we're looking for, that s is 40, and that ds dt is 0.75. What we don't have is c. So we're going to use the Pythagorean theorem again, and we're going to use the fact that the shadow is 40 feet long. And we should get that C is 50. And then we know everything except for dc dt. So what I did from here to here is I canceled the 2's. So I just have C dc dt equals S ds dt. And then I solve for dc dt, and I get that it's 0.6 feet per minute. So let's try one more. A spherical balloon is being blown up such that the volume is increasing at a constant rate of 2.5 feet cubed per minute. Find the rate at which the radius is increasing when it's 2 feet. So again, we need an equation that relates volume and radius. So you might not remember, but the volume of a sphere is 4/3 pi r cubed. Okay, so we take this equation, and again, we're looking for how fast something is changing. And again, it tells me right here that it's time. So I want to differentiate both sides of my equation with respect to t. So the derivative of v is dv dt. And then 4/3 pi r cubed, I'm going to differentiate it first as if r were my variable. And that gives me the 4 pi r squared. And then because r is not my variable, I need to multiply by dr dt. And then I need to plug in everything that I know. So this guy right here is dv dt. The volume is increasing at this rate. And again, the units, feet cubed per minute, that has to be dv dt. Find the rate at which the radius is increasing, so that's what I'm looking for. I don't know dr dt. And it being r, is 2. And again, the feet tells me that it has to be r, because r is the only thing in there that's being measured by a distance. So I plug everything in, and then I solve for dr dt. And I can either leave it as the 2.5 over 16 pi, or I can plug it into my calculator to come up with a decimal. So it's approximately 0.050 feet per minute. And again, radius is feet, time is minutes, so feet per minute. Okay, so make sure you read the book, try out some of the problems, and let me know if you have any questions. Thanks.